So next we'll look at the last infinite set that we'll consider today that is universally encountered in lower level courses, and that is the set of complex numbers. The complex numbers is the set. And the symbol for the complex numbers is an ornate or blackboard bold letter C, and this is the set of all numbers of the form a plus b times I, where a and b are real numbers, and I is the square root of -1. That is the imaginary unit. So complex numbers are linear combinations of multiples of the number I. And so as the real numbers are a subset of the complex numbers, for instance, if we allow the number b to be 0, then we have a, some real number a, plus 0 times I, and so we have a real number. So we can now show that the complex numbers is an uncountable set. And I've already outlined the proof here, as the set of real numbers is uncountable, and the set of real numbers is a proper subset of the complex numbers. The complex numbers contain an uncountable set, and so the set of complex numbers is uncountable. Okay, so quickly we'll review the systems of infinite numbers that we've considered, starting with the complex numbers. A proper subset of the complex numbers is the set of real numbers. The set of real numbers contains two disjoint subsets, and that is the set of rational numbers and the set of irrational numbers. And of these two subsets, one set is countable, the set of rational numbers is countable, and the set of irrational numbers is uncountable. The set of rational numbers has as a proper subset all integers. And for convenience, we often break down the set of integers into three sets, three disjoint sets, and that is the set of positive integers, the number 0, and the set of negative integers. And again, the set of positive integers is identical to the natural numbers. So, of these sets, we have that the rational numbers and its subsets are all countable sets, and so it is possible to form a bijection with these sets. And with the real numbers and higher supersets, well, rather with the irrational numbers and higher supersets, these are all uncountable. And so functions that map one of these sets into another is, or rather they are candidates for bijections. We'll have to demonstrate that. So when we get to the point of forming algebraic structures with these sets as underlying sets in the structure, we know immediately now which are the candidates for bijections from one into the other. All right, one more thing about sets before we move on. The idea of a deleted set. A deleted set of a given set of numbers is the set without the number 0. The symbol for a deleted set is the symbol for the set with a superscript star. So for instance, the deleted set of complex numbers is C superscript star, and this is the set of complex numbers without the number 0, but here we'll represent the number 0 as 0 plus 0 times I. The deleted set of reals is the entire set of real numbers without the number 0. The deleted set of rational numbers is the entire set of rational numbers without the number 0. And so on. The importance of a deleted set is to form algebraic structures that are multiplicative in nature. And if we talk about multiplication, we are implicitly talking about division if multiplicative inverses exist. And so these structures are important because we're going to want to be able to form combinations of them that allow division of one by the other. And certainly you cannot divide by the number 0, and so we have to eliminate that number from the set in order to form multiplicative structures, algebraic structures, with these sets as the underlying sets in the structure. All right, so next we'll look at we'll compare algebraic numbers with transcendental numbers. Alright, so one of the things that we're going to want to do in algebra is solve polynomial equations. And this immediately gives rise to two disjoint sets of numbers called algebraic and transcendental numbers. So first we'll define an algebraic number. A number alpha is algebraic if it is the solution, or a solution, to a polynomial equation with integer coefficients. Okay, so let's look at a few examples to solidify this concept. So the first example we'll look at is that every rational number is an algebraic number. And this is easy to show. For every rational number, Q, we know that that number is expressible as the ratio of two integers. And of course, the second integer in the pair is not 0. So let this number Q, which is the ratio of some pair of integers m to n, be the number x. Then n times x equals m. N times x minus m is equal to 0. And again, this number n is not 0, and so we have a very simple polynomial equation with integer coefficients. And as this number x is the solution of this polynomial, this linear equation, it is an algebraic number. And so every rational number is algebraic. As another example, we'll look at a quadratic equation. In this equation, from the quadratic formula, we know that the roots of this equation is negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Now, looking at these roots, in particular looking at the discriminant that is the term under the radical sign. We know that if this value is positive, then we have two real roots, possibly repeated. If it is equal to 0, exactly equal to 0. So in particular, if this discriminant is not a perfect square, then these roots will include irrational numbers. If this is a perfect square, then it is a repeated real root. And in fact, it is a rational number, but we've already demonstrated that all rational numbers are algebraic. And we also know that if this discriminant is negative, then the roots exist as complex conjugates of one another. And so some of the roots may include also purely imaginary numbers, in the case that the number b is 0. And so from a very simple equation, that being a quadratic equation, we see that the algebraic numbers consist of a large variety of numbers. They can be integers, they can be rational numbers, they can be irrational numbers, and they can be complex numbers, whether complex numbers including a real term or purely imaginary numbers. For example, the equation x squared minus 2 equals 0. If we solve this equation, we have x squared equals 2, so x is plus or minus the square root of 2. So this irrational number, which is a root of an integer, or a rational number in this case, is the solution to this very simple quadratic equation. And so purely irrational numbers rather, are also included in the set of all algebraic numbers. Now, at a future date, we're going to prove that the set of all algebraic numbers is a countable set. But that's for a different lecture, once we have the machinery, the tools to demonstrate that. So in contrast to the algebraic numbers, we have the transcendental numbers. And a transcendental number is a number that is not algebraic. And so transcendental numbers never occur as a solution of polynomial equations. Now, the most often cited examples of transcendental numbers include the number pi and the number e, which is the base of natural logarithms. But what we will next demonstrate is that the most real numbers are transcendental. And to do this, we'll first show that all real transcendental numbers is an uncountable set. And so I'll state this as a conjecture because we're going to use a fact that we have not yet established. So as a conjecture, we'll show that the set of all real transcendental numbers which I'll denote as T sub real, is uncountable. And to prove this conjecture, again, we're going to use a fact that we have not yet established, and we're going to assume the set of all algebraic numbers which I'll denote with the symbol A, is countable. Okay, so with this assumption, we're going to define a new set, A sub real, and this is the set of all algebraic numbers that are real, so all real algebraic numbers. Now, as we are assuming that the set of all algebraic numbers is countable, as the set of real algebraic numbers is a subset, proper subset, of the set of algebraic numbers, we have that the set of all real algebraic numbers is countable. And as we were able to see with a very simple polynomial equation, that being quadratic, some algebraic numbers, real algebraic numbers, are irrational, and so we'll denote by I sub c those real algebraic numbers without the rationals. And so here we mean a subset of irrational numbers, and those are the irrational numbers that are algebraic. Now, as this set, I sub c, is a proper subset of the irrational numbers, well, first, as it is a proper subset of the algebraic real numbers, it is countable. And just as an aside, notice in particular that this set, I sub c, is a countable subset of the irrational numbers. Okay, so we've defined a few sets, so now we're ready to explicitly state what the transcendental real numbers are. And so the transcendental real numbers must be those irrational numbers that are not algebraic. Because we're taking the entire set of irrational numbers and we're deleting those irrational numbers that are algebraic, which again happens to be a countable subset of the irrational numbers. All right, so now that we know the exact set that we're playing with, the transcendental real numbers, our claim is that this set is uncountable. So I claim that the set of real transcendental numbers is uncountable. So we're going to prove that it is by contradiction, so suppose to the contrary. That the set of real transcendental numbers is countable. Then, as the set of irrational numbers that are algebraic is countable, and we know that countable unions of countable sets is countable. We have that the transcendental numbers, which we're assuming to be countable, in a union with those irrational numbers which are algebraic, which is a countable set. This gives us all the irrational numbers, and by this assumption that the set of real transcendental numbers is countable, we have that the entire set of irrational numbers is countable. And of course, this is a contradiction. So by contradiction, the set of real transcendental numbers is uncountable. Okay, so now we need a new definition so we can make it clear what we mean by saying that most real numbers are transcendental. We will define a co-countable set. A set B, which is a subset of some larger set X, is co-countable if the complement of B and X is countable. And by this we mean that is the set B contains all but countably many elements of this larger set X. Okay, so if we take the complement of the real transcendental numbers in the set of reals, and this leaves us with the rational numbers and those irrational numbers which are algebraic, and of course this is the set of all real algebraic numbers, and this is countable. And so the real transcendental numbers is co-countable and so this is just another way of saying that most real numbers are transcendental. So in the context of solving polynomial equations that have all real roots, we are only interested in a countable subset of the real numbers, and in fact a countable subset of the irrational numbers. But as we will see, it is necessary to have the entire set of real numbers, including the transcendental numbers, in order to form algebraic structures with them, because of a property necessary called closure, but that's for a later lecture. So we'll end the lecture here today. Next time we'll dive more deeply into the set of integers. In particular, we'll look at a little number theory and explore the concept of modular arithmetic with the integers. So I hope you have enjoyed the first lecture. Thanks for watching.